Okay. So today we're going to keep talking about aquifer characterization. We'll talk a little bit more about different kinds or expected pumping responses. And then we'll do some Theis curve matching. Some business to start the day. I don't think there's any way we'll get to running this groundwater stream water interaction model, and that was one of the questions on your assignment 4. So there's basically no way we'll be able to have assignment 4 done by Tuesday. So I'm going to postpone it till Thursday of next week. So let's go ahead and put that down. All right, so let's get back into talking about and thinking about pump tests. So just to refresh our memory, remember that the idea is that we come in and we put a pump down our well and we pump the well. All right, and this well would be screened here over the thickness of the aquifer. And we draw the water down, level down in the well, and we induce radial flow in the aquifer to our well. And if we have a perfectly confined aquifer with no recharge and no leakage, we get this Theis response. All right, and that's illustrated here in this white curve. All right. If we were to plot the drawdown versus time, does anybody remember what the drawdown is? This little I mean, that's another measure. So that what you're talking about here would be R sub I, the radius of influence. That's the radius of this cone of depression here. But drawdown is not. The drawdown is, the radius of influence is the maximum extent of the drawdown. So anybody remember what drawdown is? Yeah, little s. Yeah, it's the initial head. So this was our initial head before we started pumping, right? Minus the head at some time after pumping. So it's the change here in the head. All right, so if I look at my drawdown curve here, it would start at 0 because we start off at our initial head. So this is 0, 0. And initially, it draws down quite fast. And then over time, as the cone gets bigger and bigger and bigger, the head drawdown gets sort of, it doesn't increase as fast. All right, and that's the Theis response. Yes. Yes. All these assume that we are pumping at a constant rate. Okay, so if we ended the class on Tuesday talking about, well, what happens if instead of a perfectly confined aquifer, I have this aquitard, that's leaky and adds water to my aquifer. And so here we would expect that because we're adding water from an additional source, we wouldn't see as much drawdown or change in head. And so that is this red curve here, which is leakage from the aquitard is adding water. And so our drawdown or the change in head is less than the Theis response. Okay, so I'm gonna just, I'm gonna draw one more curve here. So in all of these, at really early times, we always see a response pretty close to the Theis response. Then we get into this portion of the curve where we're releasing water from storage out of the aquitard. And then we get to this steady state leakage where the leakage out of the aquitard basically is enough to supply our pump, and we have essentially no more drawdown in our well. This transition period, this area that I've highlighted by the orange, this transition period may be sort of long, drawn out like I've drawn it here, or it could be very fast. So in some cases where we just start immediately draining the aquitard, there's no sort of delayed initiation of drainage, then we can get curves that have this early Theis response and then just go straight to, that's supposed to be flat. Let me erase it. We get this early Theis response, and then it just flattens right out. And instead of this sort of orange zone here, we go straight into the steady state leakage. So this would be an drainage from an aquitard or confining unit. With no storage. So it just immediately transitions to this steady state zone. It sort of quickly goes into this steady state. All right, so differs from the Theis response. Aquitard leakage basically inhibits our drawdown, and there is some variation in how quickly it'll achieve this steady state. So we're gonna start off with some synthetic data that'll look just like a Theis response, and then we're gonna start playing with real data, and you're gonna see that real data oftentimes doesn't look like the Theis response, but might look something like this. All right, now I'm gonna go talk about an unconfined aquifer. So you guys remember what, let's remember, what are the major ways that an unconfined aquifer differs from a confined aquifer? Yep. That's the sort of definition. What are the two ways that that really changes the behavior of the aquifer? Well, close. It's very close to that. When we pull the head down, we actually still compress the unit, but we're draining pore space. And in a confined aquifer, by definition, we're not draining pore space. So a fundamental thing is that the storage in unconfined aquifers includes two mechanisms. One is that the largest mechanism is drainage of pore space. But it also has compression of porous media and expansion of water. So very similar to the leaky aquitard, these two responses happen at different times, just like the leaky aquitard. These two responses happen at different time scales. So as soon as we turn the pump on, the mechanics of and the physics of elastic decompression is very fast. So we see sort of this confined aquifer response at early times, no matter what. So these things happen at different time scales. And process B is almost instantaneous. It really is immediate. But process A, you have to physically drain the pore space. The water has to move, and that happens much more slowly in groundwater than the pressure wave can propagate. So a general rule of thumb in, well, almost all hydrology is that a pressure wave can propagate through the water faster than the fluid moves. And you've seen this all the time, like when you're at the ocean, those are waves of energy coming in. The water isn't really moving. The water subtly moves, but it's the wave of energy that's moving much more rapidly through the water. So you see this all the time. So pressure waves move much faster than the fluid actually moves. Process A happens slowly. All right, and this is exactly analogous to the drainage of an aquitard. All right, what is the other major way that that unconfined aquifers are different than confined aquifers? So we got the storage difference. What's the other major way that they are different? Any ideas? Yeah, the thickness. So in particular here, the thickness of our aquifer changes with drawdown. So if we've got an unconfined aquifer, here's the land surface. Here's sort of our bounding unit at the base. And we got a pump in a well here. And here's our initial water table height. And the thickness of the aquifer here is B. Then we start pumping, right? And we draw the water table down and we get this cone of depression. The water table, because it's drawn down now, the thickness of my aquifer here goes to this B prime. It is now some thickness that is less than the original thickness. So, you know, recall that transmissivity is the hydraulic conductivity times the thickness of the aquifer. So what happens to the transmissivity in an unconfined aquifer as I pump? Well, yeah, the conductivity is set. It's fixed by the porous media. All right. So as the thickness reduces in an unconfined aquifer, the transmissivity reduces. So the more we pump an unconfined aquifer, the less efficient it is at transferring water. Okay, so these processes result in what we call the characteristic S-shaped curve for an unconfined aquifer. And so if we were to plot our drawdown versus time here for an unconfined aquifer, well, first of all, I'm going to plot the Theis response, because that's always our sort of standard, which with we judge everything else. And then I'll plot the unconfined response. So early times, that pressure response is dominant, and we will have an early Theis response. And then just like the leaky confined aquifer, I get this fall, my drawdown stops occurring at the same rate as a Theis response because I'm draining pores now and releasing this water. All right. But after a while, the changes in my transmissivity reduce, and that delayed gravity drainage is really far away from my well. I've drained basically most of my cone of depression. And as my cone expands, it's expanding radially very far away from my well. And I end up sort of getting a late time increase in drawdown that mimics actually a Theis sort of response here. So our unconfined aquifer gets broken up into 3 sections here. There's the early time Theis response. Then there's this section here that's the delayed gravity drainage. That's just the drainage of the pores, right? It just takes a little while for it to catch up. And then we have this late time Theis response. So our drawdown starts to increase again at later times. So in principle, for this, for these first 2 sections, if you only do your pump test long enough to see these first 2, it'd be impossible to tell a leaky aquitard from an unconfined aquifer. The response is virtually the same. And it would be up to the hydrogeologist to decide which interpretation was a better one. At some level, a leaky confined aquifer and an unconfined aquifer, it's a really gray area. They're both kind of unconfined aquifers. It's up to you to decide how well they're connected. We don't have time to get into all of the different solutions, but I do want you to know that depending on whether you think it's a leaky confined aquifer or an unconfined aquifer, there are different mathematical solutions to that groundwater flow equation that you would then use to try and interpret and decide what your hydraulic conductivity is. There's a million of them, and they get more and more and more complicated and harder to use. So the unconfined aquifer is the hardest, and you got a whole bunch of parameters you got to fit. There is a, if you become hydrogeologists, you will probably do pump tests, and you will probably have to try and interpret different well logs. There's a couple resources. First of all, you know, all of these have been published in the literature, so they're easy to find. But there's a software suite that a lot of people use. It's called Octasolve. Octasolve. Oh my gosh, I can't spell. Octasolve. And this is a well drawdown interpretation software. And it will do the Theis curve matching that we're about to do. But you could also say, hey, I think I've got a leaky confined aquifer. And you'll have to put some more parameters in there, but it'll do that too. All right, so just to summarize the different results. If I all on one plot, we're going to start off with Theis. All right, this is our Theis response. And we're going to remember that basically all of these have an early time Theis response. So the second one I'm going to plot here is a leaky confined aquifer with storage. All right, and it's got this transition period to the steady state. And then I'll do a leaky confined without storage. So it transitions much more rapidly to the steady state. And then finally, I'll do an unconfined response that would look very similar to the leaky confined without storage, but then would increase at late times like a Theis. So this is unconfined. So these are the kind of signals that we're going to look for in our data whenever we do these pump tests. And we're going to remember that all the time we get this early time Theis response. And so we can always get sort of an estimate of the hydraulic parameters by just looking at these early time data. What we won't get is a good estimate of the storage properties of an unconfined aquifer because we're not taking into account the gravity drainage. If we only fit this early time Theis, we're only thinking about the compression and expansion of the water. All right, so now we're going to talk about how we actually use at least the type curve method to calculate the hydraulic conductivity, transmissivity. So we're going to calculate the transmissivity. We can get then hydraulic conductivity if we know the thickness, all right? And then we'll calculate the storage coefficient. And the basic idea goes like this. So I'm going to demonstrate it here. And I'm going to demonstrate actually something like what you'll do in your lab. So all right, so the basic idea is this. We're going to take a type curve. So let me throw in a type curve here. I am, and we're about to do it in person in class right now. But yes, I'm recording. Okay, so this is a type curve that is the well function, WU plotted versus 1 over U. And important to note, this is the log of WU and the log of 1 over U. All right. So these are log scales. And then we take data. So let me grab some data. All right, so this is some synthetic data that I've made, all right? And I've added random error to a given aquifer of constant thickness that I pumped. It's perfectly confined aquifer of constant thickness. So this data is gonna look like Theis data, all right? And it's not real world data, and I want you to know that. All right, so, but it's useful for us right now because it gives us something that actually looks like Theis data, when our real world data may or may not. All right, so my first goal here is that the idea here is that I'm gonna overlay this curve on top of my type curve, find a best match point, and calculate all these things. But in order to do that, I need to make the axes be the same scale. All right, so the way I do that is I overlay, I get the let's zoom in here a little bit. I get the origins in the same place. All right. And then this is a little hard to see, but the bigger number is the scale for the type curve, and the smaller number is the scale for the data. All right. And all I want here is I want these hatches to line up together. They don't need to be the same number. They just need to be the same size on the scales. And so what you do, you take your, zoom out here a little bit. I'll take my upper right-hand corner. This is all laid out for you, but in the lab, but I'm just gonna decrease the size until they're about the same. And for some reason, PowerPoint moves when you do that. So this is kind of an iterative process. You can, it doesn't matter as long as they end up being the same size. So you cannot. So here we would have to, we could increase the type curve or decrease the data. So now I'm going to zoom back in. These are pretty close. So if I zoom back in, this 10 to the minus 1 and the 10 to the minus 2, those hatches are lined up right there. And if we come down here, 10 to the minus 3 and 10 to the minus 2, that hatch is lined up. So these are on the same scale now. This one, let me move it just a touch. 10 to the 0 and 10 to the minus 1 are lined up, and 10 to the 1 and 10 to the 0 are lined up. All right, so these things are scaled. The images are now scaled so they're the same size. That's all I've done. It's not perfect because I see this one is a little off here and this one is a little off here. So, you know, depending on how perfect you want to be, this probably should be reduced a little bit here. That's getting a little better. But this is close enough for our purposes right now. All right, so that's our first goal is to get these things so that they are the same on the same scale at the same size. Now I'm going to take my data and I'm going to overlay it until visually I have the best fit. All right, so you're just trying to minimize the difference between these two visually. So to me, that looks pretty close. And, you know, this is, you know, since we're not doing it with math, we're not guaranteed to all get the same answer, and we're not guaranteed to hit the minimum. But that's pretty good. And it turns out we'll all be pretty close if we do it this way. Okay, so now I've gotten my data and my type curve at the same scale. I've overlaid the data so that it fits my type curve in the best way that I can see visually. So this is called type curve matching. So all we've done is match the data to the type curve now. Okay. Mathematically, what's happened behind the scenes by doing these things is we've figured out how to map the data space to WU and 1 over U space. All right, so you know, in a linear algebra term, we've figured out the mapping between these two spaces. So now we can pick any point on these graphs as a match point. It doesn't matter, and the point on this graph that corresponds to a certain drawdown in a certain time will correspond to a certain WU and 1 over U. All right, so the point here is we want to pick a match point that's easy for us to pick numbers off of. So let me demonstrate what I'm talking about here. I'm going to add a line here. I want insert shapes line. I'm gonna draw a straight line here. All right. And I'm going to just move this line so that it hits, I'm going to move it vertically until it hits 2 tick marks. So see right there, it's on a tick mark on both scales. It's on a tick mark there and a tick mark there. That is a place where it's easy for me to know exactly what the value is on both scales. And then I'm going to put in another one. That's vertical. And I'm going to do the same thing. I'm going to try to find a place here where I hit a tick mark. So that one right there hits tick marks on 2 scales. Okay, so now I've got a match point. This right here is called my match point. And what I'm going to do right now, the first thing I'm going to do is I'm going to record WU, 1 over U, S, and T. All right, for these match points. So my value for WU, so this is 10 to the minus 1. All right, so on a log scale, so this is 0.1. So on a log scale, that means this is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So WU, so let me, I'm going to start writing out the Theis curve. I got to quit OneNote. It's giving me hassles. Oh, son of a gun. All right. So 1, overlay the data. Well, first of all, we need to ensure data. And type curve scales match in size. They don't have to be the same numbers, but they need to match in size. And that this whole resizing thing, so that the spacing between one log cycle on one is the same as the spacing between the log cycle on the other. They definitely both have to be log, and the distance between log cycles has to be the same between the 2 graphs. So overlay data on type curve and find best fit. All right, so we move the data around until it fits that type curve the best that we can fit it. Some corollaries. So least, this means there's the least space between data and curve. And we need to keep our axes parallel. All right, once we do this, we're going to pick a match point. And that's what I just did. It can be any point on those two graphs. The point has to be on both of the graphs. All right, but it can be any point on those two graphs. So I picked a match point. And now I'm going to determine one over u, wu, s, and t from that match point. All right, so as an example here, using this match point, I come over here, my WU, so this is 0.1, this would be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So as an example here, WU is 0.8. One over U, so this is 10 to the 1 is 10. So this would be 10, 20, 30. S here, S, so this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. And T, come down here, so this is 10, 20, 30, 40, 50, 60, 70. Now remember, this match point is just one that I picked. It can be anywhere where these two graphs overlap. Doesn't matter, but what you have to do is you use these lines and you pick off the values of WU, 1 over U, S, and T. Now we can use these to calculate our transmissivity. So T, our transmissivity, now is equal to the pump rate, Q, divided by 4 pi S times WU. All right, I got this and this from up here. All right, I need to know my pump rate and I can calculate my transmissivity. And then finally, my storage coefficient is equal to 4, oops, big T, little t, U R squared. So if I know the distance between my observation well and I know the pump rate and I do this curve matching, I can now calculate both transmissivity and storage. Okay, so you guys are going to do this for this synthetic data set and then for data from the Landquist well, which is a well down at Dance Hall that we did a pump test a few years ago with Cam. All right. And you're going to do this curve matching exercise. You're going to find out that the Landquist data doesn't look like a Theis curve response. And so you got to grapple with that. You can fit the early time data reasonably well. You could try and say, well, I'm just going to fit the overall curve the best I can, even though it's not going to look really good. There's a lot of ways to skin that cat. And there's no right way and there's no wrong way. All right, so I put the lab up on Moodle. It's got the Theis curve lab instructions that basically go step through what I just did. And then it's got all the curves that you need to carry out the assignment. So I hope you all, did you guys all bring laptops? All right, so let's get started. And a really easy way for me to help you guys is if you log on to the Zoom link, because then you can just share your screen and I can help you from here and I don't need to get in your face. We used to, and in the old days, that's how you did it. You would do this type curve matching on paper. But I actually think it's easier to do on PowerPoint like this. But COVID forced me to adapt the lab to the digital way, and I actually think it works better. So at any rate, it's all up on Moodle. All the data is there to download and the assignment.